Okay, so today we're going to be starting part one of the surface area calculator project, all using the TI Tiva TM123CGH6 board. As you can see, I've got Code Composer open here, and the first thing we're going to do is actually go ahead and make the project. So we'll make a new CSS project, CCCS project. We're not using a generic ARM device. Like I said, we're using the TM4C, GH6, and we have the PM. So you want to make sure you've got that set up, and we're gonna call this project just edge counter. And this is going to be the very basic, and then you want to set up your connection, and ours is the Stellaris and circuit debug interface. And then it's not giving me, normally it'll give you a little option to verify. Let me replug my board. So this normally takes a while. It's trying desperately to open up. So now the first thing that we want to do is make sure that it is actually connected to our board. And we're going to build this. I mean, obviously this won't do anything. Then once it's built, we'll go to the debug menu. And we want to make sure that we can just do anything, and that this console down here doesn't spit out any errors at us. Okay, good. So that's done. We'll exit the debug. And so the first thing that we want to do is also make sure that we have all of our includes. So the first one that you want is standard int, which has all the standard integer definitions. Then you want to also have standard bool. And the reason you want these two is that some of the TivaWare software that we've talked about before uses these inside of its own definitions. So you shouldn't have to. This way you won't have a bunch of weird compiler errors. And now you want to make sure that you include the two TivaWare things, or the TivaWare header file that gives us all the fun, useful definitions for memory locations and a couple of TI's built-in things. And now we'll save that and we'll see if it builds. And see, it didn't build, mostly because it can't find this header file here. So we're going to have to go do the same setup that we've shown previously. I have a whole video on that, so I'm not going to go over exactly what I'm doing here, but it is still the same on the current version, the version 10 of Code Composer. They haven't moved everything around yet, but I'm sure they will eventually. So you go into your include options, browse, go find the TivaWare stuff, and include all of that. Okay. And then also in your here you want to browse TI TivaWare, the driver libs, CCS, debug, and this driver library file. Okay, apply and close. And now we should be able to build just fine. Maybe not. Oh, sometimes it's a little funny about how exactly it wants this included, and it won't just include from this. It won't just include from just this. So sometimes you have to go browse. Sometimes you have to actually grab just this INC file. Did I misname this? Is that what I did wrong? You see we have a lot of header files here. I think maybe that may have been what I did. TM. Oh. No, I just don't remember how to do C. You gotta include it as a file, not as a built-in file. And then you still mess it up. I'm just gonna copy this from somewhere else, because I've obviously misspelled something. Yep, so that was misspelled somehow. But once you've spelled everything right, you should then now have this header file, and this gives you access to a bunch of TI specific functions for these boards. And then the last thing that we're going to include is another one of TI's things, and this one is from the driver library, and it is interrupts.h. We will be utilizing the interrupts on this board for this project. This one, we're just going to have very simple interrupts on port F. So, just like that, we now have all of our stuff included, and we're still building just fine. So we can go ahead and start the main program. I'm going to have everything included in the main module for now, but you don't have to do that. So the first thing we want to do, I guess I should explain what this project is. So the overarching project for this is we are making a device, an embedded system device that would be capable of measuring the surface area of products as they pass over a sensor. We're going to be using some kind of cheap photo resistors for this, but you could make it significantly more accurate with like laser detectors in a laser emitter array or some other stuff, but we're using just the photoresistors. And the way that we're going to do this is we're going to have the photoresistors in a line, essentially, and we're going to count how many of them are blocked at certain intervals based on feedback that we get from the conveyor belt itself. So obviously the first thing we need to do is we need to write a um, system that's capable of counting something, anything, based on some external information through an interrupt. So what we're doing today is we're going to write a very simple program that just tracks the number of times the switch 1 is pressed on the TIVA, and it's going to display the number of times it's been pressed on some external LEDs we have rigged up on our breadboard. We're going to count up to we're going to count up to F in hex. So we obviously have 4 LEDs, and they will represent each of the bits of the count. And we're going to count them on an interrupt, which won't look very complicated for this, but it will be essential for later stages of the project. So to do that, the first thing we're going to do is we're going to define some stuff. So, first thing we want is we want to define the edge count mod. So all this is going to do is let us reset our count when we count over the necessary number. And I'll explain that when we write the code for it. Now we want to include some interesting things from... No, we don't. We don't need to include those anymore. Never mind. And then we want to have a global variable volatile, unsigned, long falling edges. So what volatile means is that this will be stored on the board itself, and it will be stored somewhere in the RAM. So all volatile does is it says that this particular this value right here, whatever this variable is pointing to, might change unexpectedly. So just in case like something else has access to it or something like that. So that means that we can use this in interrupts and from peripherals and have it access all of those things without C wanting to freak out or us getting random crashes. So the next thing we're going to do is we're going to set up the initialization for the switches on the edge of the board, and we're going to have 2 switch functions. We're going to have S1 lets us increment our count by 1, and S2 will let us clear our count. So we're going to write a void edge counter init. Actually, we'll call it something better. We'll call it switch init. We'll call it switch init. And it doesn't take anything in. So now we're going to talk about some stuff, and I need to go open up the documentation real fast so that we can look at what all we are doing. If I can. We'll need this data sheet here, and this is the full data sheet that's loading. And we're also going to grab a pretty simple overview as soon as it lets me open it. And this I got from an EDX course, but this is just a very simple explanation of what pins are which, and I like this particular diagram here because it helps me remember which switch is which. So switch 1, as you can see, is on port F4, and switch 2 is on port F0. Now, port F0 is one of the ports that you have to unlock before you can make changes to it, because it's used in it has a very specific alternate function that we're not using, and I'm not entirely sure what it is, but you have to unlock this port and make changes to its commit register, which I'll go over right now. So then if you look over here, this is the data sheet, and we'll reference this in a little bit to talk about specific registers that we're doing when we're initializing things here. So first things first, I want to go ahead and initialize port F4, pin F4, because it's really easy. So the first thing we got to do is we do this right here, syscontrol RC GC2 register, or equals OX0000. Alright, we'll just copy that from where I have it written. So this sort of magic looking thing just tells the TIVA to turn on its clock on port F, and you have to do this before anything else, and you have to give the clock a couple seconds, a couple cycles to actually get initialized and get caught up to where it's supposed to be. So this turns on a clock for port F. And the reason it's that number is that's just how the bits line up. So if we look at the bottom 4 bits, we have this is the bottom byte of that hex number. And we look at the bits, we see that this is 2. So if you count backwards, port A at the first 0, port B, port C, port D, and then finally port F. So that just turns into 2 in hex because it's in the second nibble. And then just to give that time to initialize, we're just going to do this right here. I don't even want to. We're going to go ahead and give this its initial value. And that's really just to initialize the falling edges count, but more importantly, it gives that clock time to speed up and get ready. So now the next thing we want to do is initialize our first pin, which we're actually going to do PF4 first, which is, if you remember the document, switch 1 on the outside. So the first thing you have to do when you're initializing a switch is you have to set its direction. And we do that with the port F direction register. So this direction register essentially controls all of the pins on port F. And what we want to tell the board is that we want pin number 4 on port F to be an output, which means that we want it to be set to 0 because 0 means output. And so we'll do that with this piece of code right here. OX10. So that sets bit number 4 and only bit number 4 to 0, because when you do the Boolean algebra for this, it comes out to ANDing whatever is in this register already with a bunch of 1s, so except for the one in position 4. And again, we can look at the bytes here. we have byte 0, byte 1, byte 2, or bit 0, bit 1, bit 2, bit 3, and bit 4. So this is bit 4 we've turned on. And what we've done is whatever is in, obviously this port F direction register is a lot bigger than just 2 bytes, or just 1 byte, but we've done this Boolean operation here. And that will give us whatever these were as 0 and whatever these were because of Boolean algebra. So PF4 to input. So that's inputs, and output is obviously a 1. And now we want to tell the board not to have its alternate selection. And these, again, these definitions here are included in this file up here, which we included from the TivaWare stuff. And again, to turn off alternate selection, you want to set it to 0. Then we want to enable the digital function, which means that we're taking it as a binary 1 or 0, and that just smooths out the voltages sum for and this is the digital enable register for port F, and this will be, we want it set to 1 because it is digital, so LX1, and we can show this operation in binary as well. This is just board width, which gives us the inverse of what we had in the previous one. Just like that. So now we have the digital one enabled. Now comes a really confusing register that I still am not entirely sure what to do with it, but it's the GPIO port control register. And this register is initialized very strangely, but for this particular example we want to initialize the ones with pin F to 0. So we're going to do the AND and I'll just copy this because I get this number wrong a lot. And so here we can look at the top. So this one, the way that this register is set up is that each of the register locations has a full nibble associated with it. So this is the first nibble, and that's F0. This is the second nibble, and that's F1. This is the third nibble, fourth nibble. Well, 0, 1, 2, 3, 4. You gotta count from 0. So this is the fourth. This is the one associated with F4, and that is setting all of it, its whole nibble, to 0. And the P control is really for the alternate functions, and you'll just have to check the documentation for what it needs to be for any given function. So let me actually see if I can pull that up in the documentation. Maybe. It'll take a little bit to find it. There is a lot of information in the Alright, so here is, in the documentation, we've got the general purpose input-output, which is GPIOs. And if we scroll down, we've got the PMX bit field in this control register. But essentially what you want to do is, somewhere in here, in these documentations, it tells you what PCL actually needs to be for any given operation. And generally for a GPIO, PCL is just 0 if you're using the standard, register descriptions, data, page down. This also tells you everything about all the other registers that are involved and how they need to be set and what they do. Yeah, here we go. So this is used to configure with your alternate mode select. And this right here will tell you what things need to be for any given alternate modes. So you see if you're using UART in PA ports, whatever, you want it set to this value. If you're using this for GPIO 3, you want it set to this value. So that's all you really need to do, is just go look at whatever value you need to have according to the documentation. Read the documentation, folks. Now we're also going to turn off the analog functionality, which is another one of these control registers. There's a lot of control registers, and this is the major thing for a lot of these projects, is getting things initialized. So, and then we're going to enable a pull-up resistor. And what this pull-up resistor is going to do is ensure that the voltage is always high, because we want to trigger our interrupts later on falling edges. And the way that we want to do that is we're going to have the buttons be a high voltage, and when it is pressed it will go low. And that will allow us to see when the button is pressed and trigger an interrupt, which now we can go talk about the interrupts. We'll do that here. Copy some more stuff over. So these are the interrupt port control registers. This first one just says that the interrupt is edge sensitive. You can also have a non-edge sensitive interrupt, which means that whenever the voltage changes at all, it will trigger the interrupt. We're not triggered on both edges, which means that we're not doing, we're not just doing, we are going to do one or the other. We don't want it to change when it goes back high, only when it goes low. And that's this falling edge is 0, rising edge is 1, both edges here is 1. This is the interrupt both edges, this is interrupt sensitivity, this is interrupt edge event. This clears another important register called the RIS register, which just tells us if there's been an interrupt on a certain port and where on that port it occurred. And then this register right here is the arming register. When this is set to 1, it tells the CPU that we do in fact want to trigger interrupts from that device on that port, because there are a lot of, like I said, there are a lot of pins on the ports, and right now we don't want like PF4, well, we do want PF4, we don't want like PF3 or PF1 randomly triggering interrupts, especially considering those those are always going to be outputs since they're LEDs on the board themselves. So we don't want them doing random things. So, and now that that's done, we're going to go talk about the lock port for PF0. So like I said, the lock port, or the PF0, needs to be unlocked before we can make changes to it, and that is to prevent some of these, like specifically port C is what interacts with the JTAG debugger, and you don't want to mess that up. So the TIVA has certain ports locked so that when you make changes to them, you have to tell it you are deliberately making a change. And so that is set up with these two registers here. This is the lock register, and you say port F lock, and you put this magic number in there. That is the from the factory magic number, and you set this equal to that. You don't do OR equals. This one's is directly equal to this. And then you set the change commit register to 1. In this case, we are setting bit 0 in the change commit register to 1, so you get OX1 there. And then everything else looks almost exactly the same, except you use the number 0 bit instead of the number 4 bit. So all of these registers do the exact same thing as they did up here. They just you target a different bit, and that is just to tell the register, to tell the board to turn on those pins on the board. And then we have to do this. So these two things, this is the priority register, and you can pretty much just ignore that because priority 5 is great. Just keep them, this turns into priority 5. We can go into more in depth on how the priority register works later on, and this is the enable register, and we will go more in depth on how the enable register works in another video as well. But for right now, setting this enable register to 1, and this is setting it to 1. This is setting the port F1 to 1 specifically. Enables number 30, and well, this is the number 30 bit, and we can go look at the startup. Actually, that'll explain a little bit. So if you go into startup, you've got this this is your interrupt vector table, your nest interrupt vector table, and you see that everything in here is the default. So if we go look at port F, currently it's the interrupt default handler, and this is number 30 in the table, and you get that from the documentation. I'm gonna have to do a whole video on how to look that up and how to write that, but this is essentially turning on that bit and saying, okay, when I get an interrupt from these things, I need to go use that interrupt. And specifically, it needs to be interrupt 30. So interrupt 30 has to be turned on. So that's done. The next thing we want to do is we want to initialize our hardware that is going to display, and that's going to be on port B. And we're going to call this display init. And this is a very basic display. It's just, we just have some LEDs, and I'll show that when I get to the demo. But basically, you have to turn on the port B clock, and port B is obviously bit number 1 because 0, 1, so A is 0, B is 1, so you get 2 in this OX value, this hex value. Then we'll set this delay here equal to, actually, I don't even want to do that. We're actually just going to do the same initialization with falling edges. And again, the only reason that these are here is to give the clock on those ports time to catch up. That's it. That's all we're doing with these. Some people actually just use like a throwaway value, but I like to, if I have other assignments I can make, I just make them instead. So that's done. Then we went ahead and did the control, the commit changes register. You don't actually have to do this for port B, but we wanted to. And in this case, I have my LEDs connected to pins 0 through 3, and I just wanted to demonstrate that you can make changes to every pin at once on each of these ports. So like this says, I want to make sure all my following changes to pins 0 through 3 are allowed, set them all not to have analog function, set them all to P control equals 0, set them all to outputs so the dir is 1, and turn off their alternate function and enable them to be digital. And that's all we have to do for them, because we don't have any sort of we don't have any sort of interrupts that are going through these. These are just dumb sending electrical signals to LEDs that are wired up. So next thing we want to do is we want to write our port F handler. So These need to be, I like to name these very specifically, and they have to be static, which means that, they're global. So, um, again, I'm just copying these out of places. So, for this particular handler, got this account for balance that we'll talk about in a little bit. We'll just start that out. And we don't need these start critical sections and end critical sections anymore. I'm sorry, some of this was adapted from, this is adapted from a different project, so we don't need some of these things in here. Let's try to clean this up. And so let's talk about what all this does. So you remember I talked about the RIS? That is the raw interrupt status register. And it is a very interesting register where basically it is just a bunch of bits saying that, hey, whenever you have an interrupt, the specific pin sets its own bit to 0. So like when we press switch 1, we go back to that diagram. Go back to that diagram. When we press switch 1 on here, it sets bit 4 to 1 in this raw interrupt status. And so what we'll do is whenever we get an interrupt, we look at that whole thing and we mask out everything we don't care about. So for this one, for the first step, we're going to mask out everything except bit 4. And if this is not equal to 0, so that means that bit 4 is set in this, we're going to acknowledge it using the ICR register, which is just the interrupt clear register. And we say we want to clear the interrupt status on bit 4, and that will reset this RIS, the raw interrupt status register, to 0. Then we're going to increment falling edges, and then we're going to make sure we didn't go over the count. And you can actually do this in one step if you want, but I like to break it apart. So, but if that's not the case, then we're going to check the number 0, which is switch 2, and if switch 2 is set, we're just going to reset falling edges to 0, and that will allow us to that will set the LEDs back to 0. So that'll be important later as well. And then we have one more final kind of utility function that we have to add in here. Control copy. And that's going to be the register interrupts. So if you remember going back to this, everything was named this default handler, but we don't want to use that. We want to use this new handler that we wrote. So what you have to do is you use this, you have to turn off interrupts completely. So interrupt master disable, which again, that comes from here. Comes from this interrupt table. And it's a pretty complicated function, and it's really useful that TI included it. Then we want to register GPIO port F handler, and we want to register it at wherever the port F interrupt is in here. So what this actually does is it won't reflect here, but when it's actually loaded into code, this will now have an entry saying that we want to use this function that we just wrote to handle any interrupts that are caused on port F. And then we want to re-enable interrupts. And that's all we want to do. So now we'll go into our main, and we want to don't remember what I named this. We want to enable our switch. So switch init. Then we also want to enable our display. So display init and register interrupts. Just like that. And then all we want to do inside of the main is instead of returning 0, well, we'll return 0 if we break out, while 1, loop forever, we're just going to set the port B data register to equal falling edges. And that's all we want to do. So we're going to try to build this and see If I managed to write this much code without, yeah, that's kind of what I thought. Oh, that's not how that goes. Build again. Statement is unreachable. Yeah, that's fine. Don't care about that. 29. Expected an expression. Oh. Yeah, so this is a, because this is a macro, it can't just have that equal sign there, because what that did was that replaced this with falling edges and equals, which doesn't make any sense when we already have an equals expression. Let's build that. You got to be careful with macros. And then it's going to yell at me that this statement is unreachable, so we can just comment it out if you don't like it. Yeah. And then we'll go ahead and load our code. So I'm actually going to go ahead and add one expression here, falling edges. And we're going to see if we can get that to increment at all. Well, oddly enough, it's working. Here, I'll show you the setup. Let's see. Ooh, that looks really bad. Change my lighting a little bit. We'll set the breadboard up like this. Oh, you can't tell those lights apart at all, can you? Well, I probably should have worked on this beforehand, huh? Okay, set the breadboard up like that. And as you can see, we are getting increments, but it's kind of double counting in a weird way. And it will reset. So, now we can go back to that account for bounce function that we talked about. Oh, yeah. I'll show you this. So, this is switch 1, this is switch 2. So you hit switch 1, and it double counts to 2, double counts to 4. Actually, it double counted to 5. So yeah, it's counting wildly differently than what you would expect. But it does clear right. So the way that we're going to get around that is that these switches are really, really bouncy, which means that they when you click them, they don't like click down like they should. They don't go down and back up. They kind of wobble. So you sometimes get a bunch of extra spikes to low voltage because of the switch closing. So what I decided to do was I wrote this little helper function called account for bounce. We'll go put it up here. We'll put it above the data handler because that's what uses it. And then I also wrote another function called delay, which takes in an unsigned integer of time. And we'll put that above here. So this delay function just delays for however much time you've been given. And this thing right here is a magic number that was calculated to be roughly equal to about, I think it's about a microsecond. I'm not sure, but essentially like one of these, this takes one cycle to loop through here is what we essentially found out. So when you have this number of here, that's that number of cycles, but it doesn't take that much time. But essentially it allows you to delay for however much time you want. It's just kind of magic that was calculated and told to me by somebody else, and I haven't really questioned the authenticity of that. So you see we're delaying for 100, so it should take about 100 milliseconds now before we see any updates. So we'll better uncomment it so we actually work. So now what's going to happen? I should step through this. So what happens in this account for bounce function is um, we will unlock port F, allow changes to pet 0. Um, then we unarm the interrupts here for about 100 milliseconds, and then we rearm them. And that just says that um, don't disarm. Don't accept any new interrupts. So basically, we get an interrupt from here. We don't accept any new interrupts. Then we process the interrupt that we had. And this does slow everything down, but essentially it ensures that all the interrupts that come through, because this will buffer interrupts to a certain extent, are definitely ones that users pressed, and not because the circuitry bounced a little bit. So then we'll go back to debug over here, and we'll let it reinitialize and run. And now you can see it takes a long time. Like, it's really slow. But again, you can adjust that 100 or the cycle number to slow it down. I'm not really sure why the expression watcher isn't working at all, because obviously that falling edges is being interrupted. Let me just go to variables. Maybe it's not considering it a variable. I'll have to look into that. But what we can do is we can go to the register section, and we can go find port F, somewhere down here, port F, and we can go look at data. So currently, obviously, we're getting two high values because we have the pull-up values, and we hit that, and data doesn't change. But you can go to RIS, and so that's not changing either. So there's something wrong with this watch table, but I'll look into that and maybe post a fix to it later. But that's all I wanted to show for today, is just that this code does in fact take a number in and counts up in binary. Now keep in mind this is in binary, so you know that's representative of 4, and there's 5, and there's 6. Really cannot see the different LEDs. I should have spaced them a little bit farther apart. But we count all the way up to F. So with the red LED being the least significant bit and blue being the most significant bit. And those are just wired up from port F like you would expect. And then we can reset everything. So that's it for today, guys. I hope you enjoyed this, and maybe I will get this watch issue fixed at some point. I don't really know what's going on there. It's probably something. It's probably a debugger issue with the Stellaris interface. So we'll see. Anyway, have a good day,